Here, and I'm back with another interview question helping you break into tech. If this is your first time on my channel, make sure you smash the like button and hit subscribe. I'm Tech Pastry. I love helping you practice for interviews and make your way into tech. My job is to, as a YouTube channel, is to help you, the viewer, break into tech, and that's what I cater my YouTube channel for. CS interview questions, system design, and general background and advice for breaking in, catering your resume, how to handle the interviews, and what to expect when you interview for a big tech company, financial firm, and that kind of job. So in this interview question, I'm going to focus on number of provinces. This is a Leetcode problem, 547. This question is tagged with FAANG, financial companies like Hudson River Trading, Citadel, and I wanted to focus on this one since it's an interesting problem that doesn't use a conventional data structure like dictionaries, trees, and the like. So to start, when I get a problem like this, I like to read the problem and understand what it's asking for, and then walk the interviewer through the data structures I'm going to be using, my general line of thinking. So reading through the problem, there are N cities, some of them are connected while some are not. If city A is connected with city B, then B is directly connected with city C. Then city A is connected with city C indirectly. A province is a group of directly or indirectly connected cities, and notice that cities outside of the group are considered part of the province. If you're given an n by n matrix, where is connected for index I and j is 1, then the I and j city are directly connected. Otherwise, they're not if it's set to 0. So in this problem, they want you to connect the cities and return the number of provinces. So this on the top seems like a pretty hard question, but if you have the right data structure, then it's actually very easy. So for this kind of question, you could do a BFS starting at every at the start of every city, and then search through all of the cities that are connected with this city and add them to your horizon. And for example, if city 1 is connected with city 2, then suddenly city 2, they're part of the same set. And then from city 2, you want to continue searching all the other cities that are connected with city 2, and then add them to this set of connected cities. When you find all of them, then you want to add them all to some sort of visited set and no longer search for that. So that's one way of approaching this problem. You would need a BFS or a DFS. And to do this, you need a data structure like a queue. Another way of doing this is using a disjoint set, which is a data structure that's built on top of trees that is created by using an array initialized to the index of every the value of every index is pointed at the index that it belongs to. So when you find something that's connected, you change one of the indices to point to the index that is the next index in the set. So for example, if index 4 is connected with index 1, you'd point index 4 to 1, and 1 would point to itself. Therefore, that's the end of the set. And then if you go through here, you'll see that there are 6 sets here. You have set 0, set 1, set 1, 4, 2, 3, 5, 6, and 7. So this is another way of representing this, and you could solve this problem by going through and finding all of the connected sets, and then you just have to return a count of the sets. So we have 2 ways of doing this. I'm going to do it using the disjoint set approach because I personally think that that's cleaner, and the runtime of the disjoint set approach is O of n square, since you would have to go through the array, the matrix one time, which is n by n, and then you'd have to do the merge, the disjoint set union, which is O of n, since in the worst case you have to go through the entire set, but that's outside of the for loop. We'll talk more about Obego runtime after we're done with this. So let's go ahead and write the general function. So I'm going to name this find circle num is connected. Let's just go ahead and reset this problem. So let's create a parent, and we're going to create this disjoint set data structure for every node, for the number of indices in this matrix. So for every index in this matrix, we're going to go ahead and union them if they are connected. So we don't want to connect them if they are the same, if it's connected to itself, but we want to check if the is connected value inside the matrix is 1, and then if it's 1, we want to go ahead and union it. So I'm calling a helper function called union, and what union does is it will take the parent of the left and the right set, and if the parents aren't the same, then they want to point one of the indexes to the other index to create a union. So for example, in the array that I gave before, if we were to union index 1 and 2, we would find the parent of each index, and then and then if they're not the same, then point one of the indexes to each other. So it would find that the parent of 1 is 1, the parent of 2 is 2, and then we would point 2 to 1. So the final array would look like this, which makes 1 and 2 the same set. So how do we write this in code? We can create another function called find, and we can find the parent. That's all that find does. It finds the parent of each index, and then if we find that the iref, the index of the left and the index of the right aren't the same, then we want to set one of them to the other. So we didn't write this find function yet, so we can go write the find function, which will continue recursively going up the set until it finds that the parent in the index of the current is equal to the index, its own index. So the value of the current is equal to its own index. That means that we reached a head and we can return I. Otherwise, we want to recursively call find until we can get to the parent index. And we can make the assumption that the parent index always exists. So now that we have this union function done, after this, we can assume that our disjoint set is created properly. And I will just illustrate that by doing a print statement to show that. And I think it's very good to always write incrementally, because if you run it at the very end, a lot of things can break, and that can cause problems later on. So here, this is using an example in the diagram. You can see 1 and 2 are connected. Therefore, our disjoint set 1, 1, 2, there should be two different provinces. So now we want to count the number of unique sets, and we can do this by calling find on every set and every index, and taking the parent and adding it into a secondary dictionary. So this is adding more to the space complexity, because we can O of n, we would have the number of indices in the matrix, since in the worst case scenario, every province is unique. That I think that for the current case, I don't foresee that this matrix is going to grow ridiculously big because n is bound at 200. I think that this is a good design choice because it makes this code more simpler. It's not going to add major issues in space complexity. We're not going to blow up the stack. We're not going to blow up the heap. Like this is I think it's fine. I don't think it's going to be a huge issue if we do this. So now let's create a new unique sets variable, and we can use a default dict here. That way we don't have to do like a lot of processing. And for the index in the length of for every index inside of the disjoint set, we're going to want to add it to the unique sets, and we would find the parent of this index and then add this index to it. We don't really need, I guess we don't really need to add this. I think it's just a little bit cleaner. We can probably remove it later as we are going to simplify it. And I'm just going to run this one more time just to illustrate what's happening. So we need to import collections here. So here we have this unique set now, and we forgot to return it. So now we have this dictionary of unique sets, and we can see the parent of 1 belongs to 0 and 1, and the parent of 2 belongs to 2. And then now it's just a simple matter of returning the length of the number of keys, which are the number of parents inside of this unique set. So we can clean up the code a little bit and submit, and this should be correct. Awesome. So let's analyze the space and time complexity. So creating the parent would be O of n space, O of n time to initialize. This is O of n square to iterate through every item in the matrix, and O of constant space. By creating the unique set, we're using another O of n space, but we use O of constant time. Here we're iterating through every item, so O of n time, and then we're going to potentially add every item one time, so it's O of n space. And this is calling the find function. So the find function here has O of n because it recursively calls find. Worst case scenario, we have to go through everything once. And then the union has O of n times 2 because we're calling find twice. But O of constant space. And this is also O of constant space. This is O of n because we're going to be going through every item worst case one time, and it's going to be O of n space since we're adding every item one time. So this is a constant call. So overall, this is actually O of n square. Therefore, this entire thing is O of n square 2x O of n square plus O of n, O of n, O of n square. And the time complexities, we don't have to add the constants. It's like not that huge of a deal, but we can add the O of n. So this is the overall time complexity of this solution, and the overall space complexity is O of n, constant n square, is n square plus O of n, 2 times O of n on space complexity. So this would be how you would approach this kind of problem. So the question is now is like, how can we improve the space and time complexity now that we have working code? So let's go ahead, and since the bounds of this problem are relatively small, n at its worst case is 200, we don't have to really worry too much. This is not going to blow up in like space and time complexity. But we can always do some optimization. So how can we optimize this? A very simple trick is to do some sort of path compression in the find function. So when you find the parent of a item, you can actually set the current index to the parent and then return the parent. That way, every time you call this recursive call, the path is actually getting shorter. So if, for example, you had a disjoint set that did something like this, this is, you can see that the longest chain is 1 to 2 to 3. Every time you call find, you can actually find the parent and directly link it to 3. Therefore, this data structure is completely flat. That's a minor optimization, but it won't actually save that much time because you're compressing it. However, worst case, you're still going to have to go to every node one time. So then let's see what else we can compress or we can optimize. O of n space, can we do better than this? We probably can. We would definitely need to hold every item to make sure we don't iterate it again. One way we can do that is instead of holding a set of all the items, we can hold a set of all the parents. It won't really improve this that much because worst case we still have to find worst case we have to go through every index we have to go through every index inside of the disjoint set. Therefore, this doesn't really improve it that much, but it does make it a little bit simpler. Marginal improvements. Let's see. So this is going through O of n space, O of n time. This is calling find, which makes it O of n space. O of n time. This is actually O of n space, n square time, O of n space. Union call. So yeah, we don't really have that many optimizations. I think that we could probably do better. I can't see right now like how we can do better, but if we completely upper bound this, O of n square time and O of n space would be a pretty good solution. And we can run it again just to show that it's fully working. So the second run actually improved it a lot using the space compression. So you can see that that was like already like a huge improvement. Let's run it again just to make sure we're not, it wasn't a fluke. Yeah, it's a pretty good solution. So it's definitely fast. It can probably be a little bit faster. But for all purposes, all intents and beings, this is a good solution to this problem. So thanks again for watching. This is Leetcode number 547, number of provinces. Tech Pastry here. I help you break into tech. I cover interview problems and life on the job of a SWE. And I do system design as well. So if you haven't done so already, smash that like button. It gives me motivation to keep posting, and subscribe for more videos coming up. Thanks again for watching, and peace, guys.